1.09 seconds. And the time down, I would have calculated was how long it took to drop 18 meters, which is incorrect. It should be the amount of time it takes to drop 21 meters, which is delta 2 delta y over a square root. So 2 times 21 over 10 square rooted. The time down is 2.05 seconds. So the time of flight is going to be 3.14 seconds. So the range is going to be the time of flight times the horizontal component of the velocity. Horizontal component is 40 cosine times 17. The horizontal component, v naught x, is 13 meters per second. 13 times 3.14. So the range is 40.8 meters. Okay, that's the answer to 17. So this is the answer to question 16. This is the answer to question 17, the correct ones. Okay, when I update the exam with the new with the new questions after today's lecture, I will update these answers so that the practice test has the correct answers.
And you said you're just adding 2 more questions to the...
No, I'm going to be adding a few.
Oh, okay.
Yeah. I don't know how many off the top of my head, just however many I want to add.
Okay.
But it might be like 4 or 5. It's not going to be like 20 more questions.
And do you think that's enough time to finish? You said we'll have like around 20 questions.
You guys are going to have between 15 and 20 questions.
15 and 20.
Yeah, and you guys are going to have the entire class period, an hour and 15 minutes. So
Okay.
yeah, that should be plenty of time to do 15 and 20 questions.
Okay.
Any other questions? All right. So you can write down these answers now. When I update the practice test today or tomorrow, when I get the updated version, it's going to have the correct answers anyway. So we are continuing with our discussion of Newton's laws and forces. Last time where we left off was with what we would call our naive definition of a force, which we just said was any push or pull. Right off the bat, like I said, we know that this definition is too narrow. It doesn't include the force of gravity. It doesn't include the force of friction, for instance. Okay? So, that definition is too narrow. The way that we can work out a better definition for the force, not the correct definition, but an intermediary step, is by trying to come up with a fundamental rule regarding the motion of objects. Okay? Aristotle in the 4th century BC, so we're talking 350 BC, 320 BC, somewhere around there, Aristotle thought that a fundamental rule of motion, this is incorrect, this is what he thought, was that motion had a natural state. All objects had a preferred state of motion, which was at rest. Okay? So if I take my bag, and I put my bag here, my bag's natural state of motion is stationary. Okay? That's not an outrageous thing to think, because if you look around, most things are stationary. Not only that, but it takes me acting on the bag to get the bag to move. So I have to push the bag, I have to apply a force on the bag to get the bag to move, and then when I remove that force, the bag stops moving. Okay? Aristotle thought that the natural state of motion, remember this is incorrect, he thought that the natural state of motion for any object was stationary. Okay? In order to get the object moving, you need to apply a force. And in order to keep the object moving, you have to continuously apply a force. So Aristotle linked forces with velocity. That when an object has a zero velocity, no force is acting on it. If the object has a velocity, if the object is moving, then a force must be acting on it. When you remove that force, the velocity drops back down to zero. Okay? This is the Aristotelian idea of a force. And it lasted for a long time. Okay? For nearly 2,000 years. Aristotle was one of the first people who spent a lot of time writing down complete theories of physics. Okay? Technically at the time, science was called natural philosophy. It's just the philosophy of the natural world. And his natural philosophy, his theories of physics, lasted for nearly 2,000 years. Galileo, in the 17th century AD, okay, Galileo came around and said, this fundamentally doesn't make any sense. And the reason why it doesn't make any sense is because Galileo had an idea that Aristotle never had. Aristotle's fundamental flaw in his approach, and it was a flaw that Galileo is attributed to correcting, was that Aristotle treated everything as observational. So he approached the study of anything from an observational standpoint. Aristotle looked at the world around him, saw things happen, and formulated reasons for why he saw what he saw. And that is the extent of what he did. Once he saw something happen and he formulated an idea of why it happened, someone else might see the same thing and formulate a different opinion, and all you would do is debate the logic of your two different ideas. The scientific revolution, which occurred in the 1500s with the Copernican revolution, Copernicus said that the sun was at the center of the solar system, not the earth. The scientific revolution was a change in people's thought where they decided, instead of simply coming up with these ideas based on observations and stopping there, what if we actually tested our ideas? What if we looked at the earth around us, formulated an idea of why things happen, and then test that idea on new, unique situations that we have not seen before? The right idea will predict the outcome of the test correctly, and the wrong ideas will predict the outcome of the tests incorrectly. Okay, so that new step, that testing step, that is what's unique to sciences. At that point, science diverged from philosophy, and we no longer use the label of natural philosophy. Okay? What Galileo, his idea was what we now call the principle of relativity. Galileo's idea was that everything that you are doing in a lab, or everything, like I said, that you are observing, requires an observer. In order to measure the velocity, somebody has to measure it, right? There isn't just a velocity for the bag, there has to be an observer to measure that velocity. Okay? And there could be different observers making the same measurements. And Galileo's principle of relativity is that all observers should agree that the laws of physics are the same. Okay? The laws of physics should not depend on the observer. Okay, this is very similar to stuff that I've said already a few times, that physics should not depend on anything that we do as human beings. Right, there's the old adage that if a tree falls in the woods, no one's around to hear it, does it make a sound? According to physics, yes it does. Because the tree should do the same thing regardless of whether we are there or not. Okay? So let's imagine two observers, Alice and Bob. Alice and Bob are the preferred names for person A and person B. And let's say that Alice is an astronaut who's hanging around the sun, and Bob is just a person back home on Earth. And with Bob, there's a crate. And that crate is just at rest. Okay? Bob is going to look at that crate and radio to Alice that that crate is not moving. So the speed of the crate, according to Bob, is 0. But Alice doesn't agree with Bob, because the Earth itself is moving around the sun, right? The Earth isn't just stationary. The Earth is moving around the sun, and the Earth is actually moving very, very, very fast around the sun. The Earth is moving at about 19 miles every second. Okay? 19 miles every second. So Alice immediately radios back to Bob and says, Bob, you could not possibly be more wrong. That crate is not at rest. That crate is moving really, really, really fast. It's moving 19 miles every second because the crate is hitching a ride on the Earth, and the Earth is moving at 19 miles every second. So the speed of the crate, according to Alice, is 19 miles every second. And there is a discrepancy between their measurements. Who's right?
Both of them?
Both of them, or neither of them, however you want to think about it. Fundamentally, that question is a bad question. There is no such thing as the correct measurement of velocity. Okay? If I were to ask you which one of them is correct, the reason why either both are correct or neither are correct or there's no answer to that question is because that question is a bad question. Okay? There could be a third observer. Don't forget that the sun is not just the last thing in the universe. The sun is inside the Milky Way. Okay, so we would have the entire Milky Way galaxy, and the sun would just be one star in the Milky Way galaxy, and Alice would be there, and the sun would actually be moving at some speed through the Milky Way as the Milky Way spun. So if you had another observer, let's say Doug, me, outside the Milky Way, I would say that Alice was moving, and I would measure an even faster speed for the crate. Because not only is the crate moving with the Earth around the sun, but the sun is now moving inside the Milky Way, and I would have to add that speed to the speed of the crate. I don't know what the speed of the sun in the Milky Way is, okay, but it's fast. Okay, so the point is that all of these different observers are going to measure different speeds, and none of them are more correct than the other. Alice is not more correct than Bob. Bob is not more correct than Alice. This immediately presents a problem for Aristotle's view. Remember that Aristotle's idea about motion is based on the idea that there is a natural state of motion, that all objects fundamentally want to be at rest. There is now no such thing as an object truly being stationary. That concept does not exist. This concept of absolute velocity does not exist. Absolute velocity would be the one truly correct measurement of velocity.
So that means Aristotle wasn't taking into factor artificial boundaries?
Aristotle wasn't thinking big enough. Aristotle was thinking very, very, very earth-centric. Okay? And there were reasons why Aristotle could have been justified at his time for restricting his thoughts to the earth. Okay? At the time of Aristotle, it was a popular opinion that the laws of physics on earth for mortals were different than the laws of physics in the heavens where the gods lived. Okay? So it might have been perfectly natural for Aristotle to restrict his thoughts to the surface of the earth where mortals would live. Okay? But today, we know different. The laws of physics are the same on earth as they are everywhere in the universe. Okay? It's based on the idea that there is no special observer. If there was such a thing as a one truly correct measurement of velocity, then there would be one perfect observer, one special observer, who would measure that one truly correct velocity, and everybody else would be wrong. Okay? And it doesn't make any sense. There shouldn't be any special observer. Okay? All observers should be on equal footing in the eyes of physics. That's the principle of relativity. Okay? So, where do we go from here? Aristotle's fundamental thoughts on the nature of motion are wrong. Okay? Galileo updated his thought, Aristotle's thought, on motion to make it friendly to the principle of relativity. Galileo said that an object's preferred state of motion is not going to be at rest, but is going to be whatever it's currently moving at. Okay? So the preferred state of motion for an object will be whatever it's currently moving at. So Bob is going to look at the crate and say that that crate is at rest, and that crate is going to want to continue to remain at rest. And according to Bob, the crate does. Alice is going to look at that crate and say that that crate's moving at 19 miles per second, and that crate's going to want to continue to move at 19 miles per second. And according to Alice, it does. So they are both now in agreement that the crate is in its preferred state of motion. Okay?
Those different numbers.
Even though the numbers are different, the preferred state of motion is whatever motion it's currently in. And what a force does is a force isn't required to maintain that motion. A force is required to change that motion. So if my bag is at rest, my bag wants to remain at rest, and I need a force to change its motion from rest. According to Alice, this crate's moving at 19 miles per second. If that crate changes its speed, a force was required to change that motion. So unlike Aristotle, who linked forces to velocity, Galileo linked forces to changes in velocity. What do we call a change in velocity?
Acceleration.
An acceleration. To make the concept of a force friendly to relativity, it needs to be linked to acceleration, not to velocity. Okay? Now we have a new quantity suddenly, which is an object's inherent resistance to changes in its motion. Galileo just said that an object wants to remain in whatever motion it's currently in. It doesn't want to change from that motion. And if you try to change it from that motion, you need to apply a force on it to force it to change. It's going to resist change. Aristotle said that a force is required to maintain the motion, and Galileo says it's not a force, it's a new thing. This new thing we call inertia. Okay, inertia is the fundamental quality of an object that maintains its current state of motion. Okay, so Aristotle's concept of force is actually our modern concept of inertia.
And maintains the force?
No, it maintains the current state of motion. Aristotle's view of force is actually our modern view of inertia. Okay, where inertia is an object's inherent resistance to changes in its motion. Any questions about the Aristotelian view and the Galilean view, and why the Galilean view makes more sense in the light of relativity? And why we naturally need to arrive at this concept of inertia. Based on this new concept of inertia, we can I'm trying to think of the word. We can make better. There's a better word for that. Our definition of force. Improve. That's the word. Okay. We can improve the definition of a force. Okay. Instead of saying that a force is any push or pull, we can say an object will remain in its current state of motion unless acted upon by a force. That is a force is something that changes the motion of an object. What I wrote in red is our improved definition of a force. What I wrote in blue is now known as Newton's first law of motion. Sometimes called the law of inertia. Okay? Even though it's called Newton's first law, it's actually credited to Galileo. Okay? Nobody does all of their work single-handedly.
So you can say the current state of motion or the natural state of motion is inertia?
No, so the inertia isn't the motion itself. The motion itself is the velocity. Okay? Inertia is just the idea that an object will resist changes to its motion. Okay? So an object's inherent resistance to changes in its motion, that's inertia. But what the motion itself is the velocity of the object. Okay? So we have a few quantities that are related to each other. Okay? Motion.
So we can intertwine motion with velocity.
Exactly. Motion is a concept. Okay, it's an abstract concept. How do we measure motion in a laboratory? Velocity. Velocity is the measurement that describes motion. Okay? Changes in motion, we measure them by acceleration. Okay? Production of changes in motion, we measure that with a force and resistance to changes in motion is inertia. The thing on the left is the concept, that abstract concept that we're trying to describe mathematically. The thing on the right is the mathematical measurement that we would make in a laboratory that captures numerically that abstract concept. Okay? Any questions? A lot of work that went into the preliminaries of physics, the foundations of physics, was trying to decide what the correct quantities were to measure to capture these abstract concepts. That if you wanted to describe an object's motion, why should you measure its velocity? That if you wanted to describe an object's production of changes in motion, why should you measure a force? Okay? There was a lot of work that went into choosing the correct mathematical quantity that went with the correct concept.
So technically, let's say the markers that are on the table right now, technically, so would the table be inertia because it's acting upon a force?
No.
Go down? Or?
No. The table would have inertia, but the table itself would not be the inertia. The table would be a table.
Okay, but
Inertia is
it
the
has,
resistance.
what you're saying, it has inertia?
Yeah.
Okay.
Inertia is a quality that objects have.
Okay.
Okay? Inertia is an object's inherent resistance. So this is a possessive.
So you can say characteristic,
What?
a characteristic of an object.
It's a characteristic of the object. It's a quality of the object. Okay? It's a fundamental thing that that object has.
So can an object have more inertia than, like, let's say, than other objects?
Exactly. Objects that have different amounts of inertia. Absolutely. Okay? This table is going to have a lot more inertia than my phone.
Yeah, because the resistance.
I can
the
push
weight.
on my phone
Yeah.
fairly lightly and change its motion. Phone's not moving, phone's suddenly moving.
Gotcha.
But if I try to push on the table with that same force, table's motion's not going to change. The table's got a lot more inertia than the phone. It's also the table's bolted to the floor.
Or
Okay,
weight.
so that helps.
Or weight,
Hmm?
or weight.
Weight is different. Okay, so weight has nothing to do with inertia actually.
Okay.
That I'm going to get to. Okay? For now, this is what we have. I haven't introduced weight yet. Okay, we are getting there.
Okay. I don't wanna get that weight.
Any other questions? Okay. Now, there's a problem with this improved definition, which is that it's actually too broad. Okay? Our original definition was too narrow. Our new and improved definition is too broad because our new definition includes these things that are called pseudo forces. These things that are like forces but aren't real forces. Okay? A pseudo force. The prefix pseudo means like but not quite the same as. Okay? A pseudo force is something that acts like a force but isn't. I'm going to put an asterisk there, and I'm going to expand on this in a second once I improve on our improved definition. I want to whittle down the definition of a force to the final version of it. Okay? A force fundamentally needs to describe an interaction between objects. Okay? When I push something, the force is an interaction from my hands to the object that I'm pushing. So if I'm pushing this screen, there's an interaction from my hand to this screen, and that's what the force is. The force is that real physical interaction between those two objects, my hand and the screen. When I let my marker go, there is a real physical interaction between the earth and my marker. It's mediated through the force of gravity. Okay? If the earth vanished, then when I let my marker go, would it fall? No. The earth needs to be there to pull the marker down. Okay? Forces have to describe real physical interactions between objects that change the motion of an object. Okay? Or at least that have the potential to change the motion of an object. Just because I apply a force on an object doesn't mean I'm definitely going to change its motion. Right? Like I said, this table right here, I can push on this table as hard as I want. The table's motion is not going to change. That's because it's bolted to the floor. Okay? But my pushing is an interaction between my hands and the table, and my pushing does have the potential to change the table's motion. Okay, so the correct definition of a force is going to be an interaction between two objects which has the potential to change the motion of the objects. Okay? So this asterisk for a pseudoforce, something that acts like a force but isn't, what's different about it? A pseudoforce is not an interaction between two objects. A pseudoforce will change the motion of an object, but it will change the motion of an object without there being any physical interaction. A pseudoforce will change the motion of an object without there being any physical interaction. The W/O, that's just with that, for short. Yeah. No, gravity's a real force, okay? It's not a contact force. It's a force that acts over a distance, okay? But it is a real force. I'll describe a few pseudoforces.
Wind, is still
No,
visible?
the wind is still a physical force,
Yeah.
okay? Because the wind, even though it's invisible,
Right.
the wind is an actual physical substance that's there. You can measure how much air you have. That air is going to have physical properties like inertia, and that air can act on like a sail in a sailboat to change the motion of the boat. Okay? Let me give you some examples of pseudoforces. A very common example is if you guys are driving in a car and you turn the car at high speed what happens to you?
You
Change
jerk
direction.
left the opposite direction.
You're pushed out away from the center of the circle. Okay, so if you're turning in a car, you feel a push away from the center of the circle. But no object is actually pushing you. That push that you feel is a pseudo-force. Okay? You will be, when you're driving the car initially, at rest inside of that car. Your butt's firmly in the seat, you're not moving in the car, right? So you can have an observer, somebody in the passenger seat. The observer's looking at you, you're not moving. But when you turn, suddenly what happens is you slide in your seat. Your motion has been changed. But your motion has been changed without any object interacting with you. No object is physically pushing you away from the center of that turn.
Just a force.
It's a pseudo-force, it's not a real force. A real force requires an object to really
Physical,
push you,
physical encounter.
okay? There's no ghost that comes by and pushes you. It's not the wind that's pushing you. There's no giant magnet outside of your car that's pulling you. Okay, there is no physical interaction. Okay? What causes the pseudo-force is the fact that the car accelerates in the turn. Okay? Anytime an object is turning, it's accelerating. Remember that an acceleration is a change in velocity. Velocity is both speed and direction. So if you turn, your direction is changing, and therefore that object is accelerating. So let's imagine your car. Your car is driving forward. So according to Newton's first law, the car wants to continue going forward. This is the path the car wants to take. Okay? Where did I put them? Now, here you are in the driver's seat. You are also moving forward. So, according to Newton's first law, you want to travel in a straight line. You don't want your velocity to change. So this is the path you want to take. Or you could think of it as the path your body wants to take. Okay? Now, the car turns because when you turn your wheel, when you turn the steering wheel, the tires on the car turn. The tires are built specifically to generate a lot of friction so that the car will not slide when the tires have turned. The only recourse for the car is to change direction. When the tires turn, the road will put a force on the tires, and that will change the direction of the car. But you are not physically attached to those tires, so that force does not act on you. That force acts on the car. So the car is going to turn. This is the actual path of the car. Okay? But you are still trying to travel in the same direction. No force has acted on you. So you are still trying to travel in the same direction. So the car is turning, but you are trying to still travel forward. You experience that inside of the car like something is pushing you, but in reality, you're just trying to travel in a straight line. Yeah.
It's the same thing as if we were in a car and throw a ball up, and we would take the curve, and the ball would keep going straight.
Exactly.
Before we go.
Exact same thing. Okay? if you drive in a straight line and you hold your hand out of the window and you throw a ball up, it looks like the ball travels up and down, as long as the car is traveling in a straight line. But if you're throwing the ball up and down, up and down, up and down, and then suddenly when you throw it up, someone turns, from your perspective, it looks like the ball suddenly flew away from you. It looks like the ball was suddenly pushed away from you.
Right.
Okay? But it's an illusion. It's not real. Nothing really caused that ball to fly away from you. You moved away from the ball.
Because of the concrete, the floor caused the force on the car.
Yes, because the car itself moved. Okay? So the car experienced a force that caused it to turn. But you are not part of that car, so you don't experience that force. You are trying to travel in a straight line. And as your body tries to move in a straight line, from inside the car, it's going to look like you're being pushed out of the way. Okay? This we call the centrifugal force. It's not a real force, it's actually a pseudo force. Okay? Centrifugal comes from the Latin centrum, which is the center, and fugus or fugi or whatever, which means to run away from. Okay? You're being pushed away from the center of the circle. Yeah.
That's from the other car?
Can you say that again?
Is that from the other car turning? That's from the other car turning?
It's from the car accelerating, yeah. It's from the car turning.
Okay.
Okay?
So centrifugal, sorry.
Go ahead.
Centrifugal force is a pseudo force.
Yes.
Damn. So, would you say that you're based on your environment and the car that's turning, you as yourself, couldn't the environment make you a part of the car? Say you have bucket seats, now
Yeah,
you
eventually what's going to happen is you'll slide somewhat, but eventually you'll hit the door, or the seatbelt will lock tight, and then that will apply a real force on you, and that real force will change your motion and put you in line with the car.
Gotcha.
Okay? So you will experience two changes in motion. The first, when you turn, you slide out of your seat, that's a pseudo force. Second, you'll push up against the door, and that'll turn you in the direction of the car. That's a real force, because the door is a physical object that you're pressing up against. Okay? So you experience two changes to your motion. One is caused by a pseudo force, one is caused by a real force. Okay? Now, let's imagine something a little less practical, but no less real. Here's the Earth, and let's imagine a very, 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 very tall building. Like a building that goes out into space. Okay? This building doesn't exist in real life, but I can imagine such a building. Okay? And I want two observers again, Alice and Bob. I'm going to say that Bob is up here at the top of my very, 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 very tall building. Okay? And then Alice is in outer space, watching Bob and the building. Okay? Before Bob rides up that elevator in a really tall building, Bob makes sure to paint an X on the floor. And what Bob is going to try to do is drop a ball off the building and hit the X. Okay? Now the problem is that ball takes time to drop to hit the X. And because the building is so tall, it takes a lot of time for the ball to fall and hit the X. The Earth is not stationary as that ball is dropping. The Earth is spinning. So as the ball drops, and Alice sees the ball travel in a straight line, the building rotates with the Earth. No force is acting on that ball other than gravity, and gravity's pulling it straight down. So that ball's path, according to Alice, is going to be a straight line. But according to Bob, the path of that ball is not going to be a straight line because the ball is going to get progressively farther and farther and farther away from the building. Right? Initially, the ball is close to the building. Initially, the ball is right next to the building. Then, the ball is farther away from the building. Then, the ball is even farther. Now, the ball is really far away from the building. And look, it's going to miss the X by a long shot. The ball falls straight down, but as the ball is falling, the building is moving away from the ball.
But not enough for us to notice, right?
We're imagining a really tall building. And yes, let's imagine that it takes like half a day. Not half a day, that's too much. But let's imagine it takes like an hour for the ball to drop. Okay? In an hour, the building is going to move a significant amount of distance. 1/24 of the whole circle. Yeah.
But isn't
The ground is moving with the building.
So why would it
Ball is in air while
The ball isn't touching the ground, right? When Bob is holding the ball is somehow connected to the ground. But the moment Bob lets go of the ball is no longer touching the ground. The ball is no longer touching the earth. So as the earth rotates, why should the ball travel with the earth? The ball's not touching the earth.
Yeah, there's no physical force guiding it.
Just gravity, but
Yeah,
gravity
just
pulls
gravity.
it straight down.
Just-
So the ball should travel, according to Alice, in a line straight down. Right? But according to Bob, I don't have a lot of room here to draw a Bob's perspective. But according to Bob, the ball travels along this path. So it seems like there's a force pushing the ball away from the building, but there actually isn't. There is nothing causing that ball to rush away from the building. There's nothing pushing that ball away. It's the building that's moving away from the ball. Okay, this is a pseudo force. And this is called the Coriolis force. And once again, it's called a force, but it's not a real force.
And that's like before coming into play with like air, I guess like air resistance, like wind, how the wind moves and
Yeah,
stuff like
you
that.
can imagine this happening in a vacuum, and it's still going to do the same thing.
Uh-huh.
There's no air necessary to blow that ball away from the building. We're not talking about anything like that. We can imagine that there was no air whatsoever, and we would get the exact same result.
Would we be able to see this in a lab or no? We
Yes,
can do that. We can-
absolutely. It would just be a very small amount. Okay? If you were trying to launch projectiles over far distances, like a battleship trying to launch artillery over a couple of miles, that artillery is going to spend a significant amount of time in the air, and as that artillery is flying, the Earth is rotating underneath it. So if this is where the target is and you fire at the target, as it travels, the target's actually rotating out of the way. So you need to aim not at the target, but where the target's going to be. You have to take into account the rotation of the Earth. That's the Coriolis force. Coriolis force is also responsible for causing hurricanes to spin. Okay? It is not responsible for causing the toilet water in your bowl to spin. Okay, that was a joke on The Simpsons from a long time ago. But it is responsible for hurricanes spinning. It affects hurricanes because hurricanes are extremely large objects. It would not affect them if they were small. So here's the Earth. Okay? And let's imagine that a hurricane's bottom part, its southernmost part, was at the equator. So here's the equator. And the hurricane's southernmost part is there. And then the northernmost part of the hurricane is up here at some other latitude. Okay, that's the hurricane. If the Earth is spinning like this, then every point on the Earth is moving to the left. Okay? So the bottom part of the hurricane is moving to the left. The top part of the hurricane is moving to the left. What's important, though, to understand is that every point on the Earth has to complete one revolution in the same amount of time, one day. Whether you're near the pole or near the equator, you have to travel in one full circle in a day. Look at the size of the circle at the equator compared to the size of the circle near the pole. Which one's bigger?
Equator.
The one at the equator. So the objects at the equator must be traveling faster than objects near the pole. So the bottom part of the hurricane is traveling faster than the top part of the hurricane. And as they travel, the bottom part passes the top part. And you get this clockwise rotation.
Is it as it passes?
The bottom part is moving faster than the top part.
Right.
So it looks like it's doing what, actually from your perspective, it looks like it's doing this. Okay? So there's a clockwise rotation in the northern hemisphere. In the southern hemisphere, you would get a counterclockwise rotation. Look up any picture of a hurricane. You'll see that it rotates clockwise. Okay? That's the Coriolis force. Okay? Any questions?
So basically physics is taking math and applying it to real life.
Yes.
Love that.
Any other questions? All right. I want to write down Newton's second law and Newton's third law really quickly because we're running out of time here. We have 10 more minutes. Newton's second law is an equation that describes the relationship between forces and acceleration. Like I said, Aristotle had related forces to velocity. Galileo said the proper relationship is forces to acceleration. Newton's second law provides that relationship. It's important, though, to understand that no single force causes an object to accelerate. Okay? It's the cumulative effect of all forces on an object that produces the acceleration. if you had a game of tug of war, so here's the ground, here's the rope. Tug of war typically has like a little flag, okay? And you want to pull the flag onto your side of the field. If there was one team here pulling to the left, I'll call that force 1. Does that force guarantee that the flag is going to move to the left? No, right? That single force does not determine the flag's motion. It's the net effect, the cumulative effect of this team's force and this team's force. Whichever force is greater wins. And that will determine the direction that the flag moves. So it's not a single force that determines the acceleration on an object. It is the cumulative effect of all forces, what we call the net force. So the net force on any object is related to the acceleration of the object, but there is a quantity that relates the two. That quantity we call mass. Okay?
The quantity is the relationship.
Yeah. What we would call a proportionality constant. Mass is a measure, sorry, not a measure, the measure. I don't want to imply that there are multiple. The measure of an object's inertia. The larger the mass of an object, the more inertia that object has.
So would it be wrong to say that mass is related to weight?
Weight depends on mass. Mass does not depend on the weight.
Okay,
But we haven't talked about weight yet.
yeah, okay, but weight is a measurement of mass, right? So
Mm-mm,
grams,
mm-mm.
kilograms.
No, weight is not a measurement of mass.
Oh no, wait, the opposite. That's
No. Mass is also not a measurement of weight.
okay.
Weight depends on the amount of mass that an object has. The more mass an object has, the more weight it has. The reverse is not true.
So then
Mass is not dependent on how much weight an object has. Okay, mass is a fundamental quality of the object. Okay? But once again, I haven't mentioned the word weight. We're not there yet. Okay, we still have a little bit more to do before we talk about weight. But if we have two objects, let's imagine them object A and object B. Let's say that object A has a mass of 1 and object B has a mass of 5. We're not worrying about units right now. And on both objects, I apply a force of 10. What's the acceleration of object A going to be? According to Newton's second law. Imagine that this is the only force on the object.
10?
10.
The acceleration is going to be 10 on object 1. What's the acceleration on object B?
2.
2. Look, the object with less mass has a larger reaction to the force. The object with more mass has a smaller reaction to the force. So the object with more mass has a greater resistance to changes in its motion.
That doesn't, we're not talking about weight, but that depends on the shape too.
I'll talk about mass in 1 second, okay? It's much more fundamental than that, okay? But as mass gets larger, okay, the acceleration gets smaller. More mass, more resistance to acceleration. And resistance to acceleration is exactly what we call inertia. So mass is just a measurement of an object's inertia. Okay? The correct thing that determines the amount of mass that an object has, not what mass is, okay? But how much mass an object has. I don't want you guys to confuse these. What mass is a measure of an object's inertia. How much mass an object has is directly related to how many protons, neutrons, and electrons that object is made out of. Okay? All matter in the universe is made up of protons, neutrons, and electrons. Every single proton in the universe has the exact same mass. Every single electron in the universe has the exact same mass. Every single neutron in the universe has the exact same mass. So for any object, if you count up the number of protons, the number of neutrons, and the number of electrons, that will tell you how much mass any object has. Okay? The question, why does a proton have the amount of mass it has? Why does a neutron have the amount of mass it has? And why does an electron have the amount of mass it has? That question is way beyond the scope of this class. Okay? Why an electron, a proton, and a neutron have a certain amount of mass, that was proven theoretically in 1964, and it was proven experimentally in like 2012. Okay, it was literally, it just happened. Okay, that was with the discovery of the Higgs boson in CERN. Okay, so that is way beyond the scope of this class. Okay, really quickly, what weight is, this is gonna be the last thing. Weight is the force of gravity near the surface of the Earth on an object. Okay, so if you have an object that's falling freely near the surface of the Earth, you just have a ball with some mass m. Here's the surface of the Earth, and it's falling. No air resistance, no anything. The only force acting on it is gravity. We call that force weight, W. And what would the acceleration of the object be?
1 times the mass.
Gravity.
If it's just an object
Oh,
falling,
same thing.
Gravity.
9.81, right? It's G. So according to Newton's second law, the net force on this object, which is just W, equals the mass of the object times G. So the weight of any object near the surface of the Earth can be measured by m times G. But weight is the force of gravity near the Earth's surface. Sorry, promise this is the last thing, the units. The units of force we call newtons. The units of mass in the SI unit are kilograms. Gram is the metric unit of mass. The SI unit is kilograms. So if we have an object whose mass is 1 kilogram, what's its weight? 1 times 10, 10 newtons. Okay? So weight depends upon mass, but mass depends upon how much matter is there. How many protons, neutrons, and electrons. Okay? And weight is simply a measure of gravity near the Earth's surface. Weight is a force. Mass is a scalar, and it's the measure of an object's inertia. So mass has to do with the motion of an object. Weight has to do with the gravity acting on the object. Those are two completely different concepts. Okay? We're going to talk more about this next time. Okay, so Newton's first law and Newton's second law.